Yeah, but it's working very nice. Now I go new, Simulink model.
Blank model.
Yes, blank model. Then it's better to switch off this automatic time. Okay, let's go through all this process once more because, well, it's not a big deal, but I will not, because yeah, see, this remote life is funny, yes, because the biggest problem I see is that students cannot help each other. This is the biggest issue. Like, this makes a lot of problems. Okay, I will now put somewhat minimize. Okay, I can switch this off. What I do first, always, I go to simulation and model configuration parameters. And here go to the fixed step and no continuous states. Here we could leave like 10 seconds for a while, not a big deal. Later we will update this. Second thing you should do is to save your model because it could crash. And of course, if machine restarts, you will lose your work. So one of the, but there is no way to save it somewhere on the network drive. So you must be like very careful to not compromise this computer, but sometimes it uses to restart. As much as I know, Astil last time lost his work.
Yes, now I am using my own computer.
Okay, you can save anywhere, but anyway it will be deleted on restart. So doesn't matter where you save it. Just you have to find it, and you say lab 4, for example. Okay, the keyboard. Okay, it's very slow but working. Save. Now let's build this PLL. PLL building. It's funny thing. So you need to build this circuitry in accordance with all this schematics. I will look to the schematics into my another computer to not switch very frequently between. Okay. Oh, this AnyDesk is not that bad. Because I was expecting that it could be slower. Okay, let's go here. Let's go to the lab work description. PLL. So basically, it's not a big deal. Yes, this is like the model consists from something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 blocks. Yes, this is like very simple thing. So we will start with okay, let's open the library here and find all these blocks. And then we will later configure them, but we will start with putting them on the table. So I will go and put here this multiplier, which is a phase detector, yes? And this is just a simple multiplier block. From this is from the multiplier blocks, we go to the two gain blocks. First gain block, second gain block. So if you wish, you can rotate them. But okay, because otherwise you will have very format, rotate and flip clockwise, format, rotate clockwise. Okay, just I rotated in the wrong direction. There is even some shortcut, Control R. So if I press Control R, it rotates. Now we have two sums.
So the first block you put was product, right?
Yes. Two sums. You can use round sums but we need the sums. Okay, if you wish that sum is square, rectangular, this is the first thing what you wish, then maybe we could remove this pipe here. Then it will distribute all inputs evenly. And what we will also wish to mirror this block, because normally signal passes from the left to the right, but because we have loop, we will mirror those blocks like flip, yes. And I will just copy paste this block. Because we need several sums. They must be put somehow, they do not cross. And now, then first gain go to the first sum and goes to the multiplier. And second goes from the first sum, from another sum. One of the inputs go to the same signal. And here we put this. This is a just proportional controller, so-called. This is so-called coefficient K1. Yes, and there is another coefficient K2, and these coefficients must be calculating according all these big formulas from the lecture slides. So here, of course, you can put just direct numbers, and we will do this in contrast to we have done before, then when we did some calculations and put here some formulas, but we will just directly enter the values. So we will simplify our life. And this is another, this is ideal integrator. And ideal integrator needs delay here in the middle. Just we put delay block. Again, flip it. This is Control L, I think. Or Control. Okay, I will select Control L. Or it's Control I. Yes, it's Control I. Ah, okay, I did it. I do not need to flip it, sorry. It was my mistake. It doesn't need to be flipped because it goes like this. This is a digital filter with recursive digital filter with coefficient A1 equal to 1. This is so-called ideal integrator. And next, signal goes to this voltage controlled oscillator. Here I just look for the discrete time VCO. I will just enter VCO here. It comes from kind of DSP library. And
Professor, I have one doubt.
yes.
What are these two blocks below that gain? What are the names?
They are sums.
Ah, okay.
You just have to configure those sums. I just have shown. I will not go back and repeat this 10 times. You can later look to the video if you wish, but I will go forward. Or you follow me or you do it yourself, but yeah.
No, I'm just following your professor. Like I am doing simultaneously and just following your guidance, professor.
Okay. So I have shown how to get this.
Yeah.
It was around at the
like
beginning.
SUMS, it's not there in that library manager.
Okay. And now I find this discrete time VCO. Yes. Put it here. And also flip this block, Control I. So I'm sorry. Yeah. Okay, let's go to the funny things. So we connect this VCO. And now this VCO must be inverted. So theoretically, you can put here phase minus pi or something like this. and then it will invert the signal without this additional block. We could experiment, but if you do not wish to experiment, just go and select this gain block, which inverts the signal from the VCO. Just put it here, invert it. Flip and put here -1. Actually, what it does, it just inverts the signal. Without this, it will not work correctly. So in fact, this is PLL. Yes, we already made this phase locked loop. This is this loop, but we have to feed something into it, and we have not configured it yet. Let's save it. In just a moment, I will come and we will continue. Okay, the next step is, let's maybe discuss about these configurations here, because we now have to configure all this stuff. So if we go to the description of the lab work, we will see that we will need parameters K1, K2. This is the first gain and the second gain. This is two parameters which are needed to be calculated using some sophisticated formulas. And also in the VCA gain, we have to configure it correctly. In the lab work description, it is already said, if you read it carefully, it says input sensitivity must be K0 divided by T. Yes, and then we need these parameters T. So what we could do, we go to MATLAB and define some parameters according with our student ID. Yes, first thing we define this T, which must be equal to our student numbers, last three numbers, plus 1. Okay. My student number is $291,0058. So this capital T is equal to the 58 or 59, because I have 58, but you have a completely different number. This variable must be defined. Center frequency, this you can call it as you wish, but this center frequency must be equal to your to 1 divided by t divided by 1000. So actually that means that this frequency is like you have very small step. Okay, it's microseconds, by the way, so we need to put microseconds. So it is e minus 6, yes. 59 microseconds, because it is a step at which we sample our waveforms. This is a sample rate effect. Yes, this is a small step between samples into this simulation, actually. And next thing, what we do here, we now say the frequency, this frequency of the sinusoid, which is generated by this VCO, because actually what this loop does, it synthesizes some sinusoidal signal here, which could be used in the receiver to get accurate tuning on the station, yes? And here I feed the reference signal for the fine-tuning this loop. So it is just, it ensures that frequency of signal coming to this port and generated frequency is exactly the same, and the phase is exactly the same. Why it's needed, why we cannot take directly this signal? This is because sometimes we need to generate sinusoid, but reference signal could be not sinusoidal, or it could be, for example, modulated. Or also it's possible to for example, put some divider here. And then in this case, this PLL could generate n times higher frequencies than reference. This is particularly used, for example, in your computer and mobile phones for generating much higher frequencies than your crystal oscillators are. So, for example, you have a crystal for, let's say, 10 megahertz in your computer, but your processor is working at 2 gigahertz, yes? There is no crystals for 2 gigahertz, forget about it. There is a tiny PLL chip into your computer, which generates 2 gigahertz and then compares signal with crystal coming here 2 megahertz, but here is divided 1000 times. So it ensures that generated signal, this clock for the processor is stable. Otherwise, you will have no way to generate stable signal for 2 gigahertz, yes? And if you put this some configurable divider, yes, that you can manipulate it from BIOS, for example, you can change the clock of your processor without actually replacing this crystal oscillator, yes, because you can modify the dividers and you can overclock or underclock your computer and so on. So PLL has this very, very broad use, not only in communications. Okay. And now this is a frequency which have to generate. It is exactly 1000 times higher than this sample rate. That means that this frequency is just 1000 times yes, 1000 times lower, yes, because we need it, and in this case, it will ensure that your generated signal has exactly 1000 samples, yes. So it's well sampled. This is one of the conditions for PLLs. It must be well sampled, otherwise it will not synchronize and will start to be weird. I have experimented a lot with this to ensure that it goes well. This is calculated automatically. This damping rate or damping ratio, this is some typo here. This zeta is equal to your also student ID, but it must not be larger than 2. If for some or 3, and if you have some student ID larger than, but I think the maximum numbers is like 200 something, then you who should say me, and then we will add 0 on the front. For example, my student number also is 921. So
Professor?
the damping, sorry?
Professor, like what is this one, like before the discrete time BC, it's -1 something is there? What is the name?
Again?
In the
It's
block
gain.
diagram.
Gain.
It's gain, but we need to flip. It's -1. It has been written there.
We should put minus instead of 1. We should put -1.
Okay, okay. We need to change in the properties, right?
Yes, this is very simple questions. You are not familiar with Simulink at all. You should practice in this case because we cannot solve such simple problems. Yes.
Yeah. Okay.
Go and take some courses. I don't know, because this is a basic questions. Yes.
Okay,
This
okay.
is the gain block.
Professor, our number is 201.
Okay, let's check. Maybe 2.1 still works. It will be like very heavy, but maybe it would work. Let's check. If it will not work, then we will decrease to 0.21, but it will be then too small.
But I think it's not working. I checked before, but it's not synchronizing.
Not synchronizing. And what
Can I-
happens? It still becomes loose.
Can I show you?
Yes. Okay.
Okay.
Okay. And what happens if you run? Could you make it larger? I do not see it. It looks like it goes exactly in opposite. Okay, please show me the diagram. This is the -1. Yeah, if you put zeta1, does it synchronize this? Just put 1 there and that's it. Okay, let's run. Okay, how much is it? How your simulation? How long is your simulation? Okay, 20. Put 200 there. And then run. Let's look to the final state. It starts it goes. No, it doesn't synchronize. Yes, it goes to the wrong direction. I think you have some mistake. go to this. This is a capital T, yes. Initial phase, sample time, seconds, FQ, output amplitude, K0 -1. Okay, and what's the frequency for this sine wave block? Okay, this is nice. Because it looks like you have, it goes to the wrong direction. It seems like or either K1, either K2 is not correct. Okay, let's do your variant and we'll check.
Okay. I have used this formula to find K1 and K2.
So, okay, just a moment. I will look to my notes. Okay, where is it now? This is the SDR models, PLL. PLL init. Okay, so let's look to the script. Okay, I have such a script. Okay, I will paste it directly here. Okay, just new script. Paste. Okay, you have ABC. What is the number?
201.
Okay, and the first one?
XYZ 009.
Okay, it's just 9. Is K1 and K2 same? Looks same, yes. It's you. I have 1.5067. What you have?
No, but we changed zeta, right? To 1. So it will be different.
I change zeta to 1. 128 0.4.
Yes.
That's correct. What's the frequency? 100 hertz. It's correctly, so strangely that it doesn't work.
And but is it because I have changed this one? was supposed to be.
No, but this is just, you see, this is, yeah, but this is just a reference signal. It must be like its derivative.
To make the amplitude same of both signal, I changed to, instead of 5, I used 6.3.
Yes, but it will just change amplitude, not the phase. But okay, it's minus.
No.
That's a reason. Yes, now it's working. You can switch back to 20, but I clearly see that it works. Because it generates correct signal, just this comparison scope was not correctly working. I just was looking that it's exactly, you see, now it catches this signal and keeps together all the time. Okay, we fixed your problem. And you can try the real zeta now. It will be much slower converging, I think. Let's look what will happen. No, it's even faster. Okay, good. Very well. So it's working. You see, that's nice. Okay, let's go back. So now I have this script. So thanks to the still now I'm just too lazy to put everything by hand. So I just put the script, but actually what it does, it calculates all work accordance with this formulas which I have put into the orthos page. This is, if you go to the lecture slides, like if I go to lecture slides here, if this we have PLL design lecture, and here we have these formulas for the calculations of all these parameters. This is like, we use these formulas, we calculate this, I don't know, this is kind of this. This is this zeta, but this is, I don't know what is this for Greek letter, eta or something. I forgot. Astil said to me what.
Eta.
What?
Eta.
Eta. Okay, this is eta, yes. And this is just temporary variable to simplify all these formulas. And then you just put everything. And actually what you have to find, this is only one K1 and K2, yes? Because this is necessary for this. Here you put this K1 and K2. And actually, if you have calculated, you can just copy this value and just directly enter here, K1. And K2. And of course, this is not that versatile compared to the script, because if I now change zeta, then it will not, you have to manually update this value. That's a better way, is just instead of entering the number, I just put the variable K1 and K2, and these variables are calculated in the workspace. Or you can even put this script into some callback function, and then it will be run automatically, because otherwise you have to run the script by hand before they're running the model. And also, if you give it to someone else, you shouldn't forget to give the script. Otherwise, this person will not be able to run your model. So the better way is just take all this script, copy and put into the file, model properties.
Professor, you are not sharing screen.
Yes, sorry. New share. So you have this script, yes, PLL init, with all this stuff working. You are sure that it works. You can do later, copy this stuff, and then go to the file, model properties, and there is a callbacks, and put it into the init function. Just paste here. And this init function is run always before running the model. And it keeps together with this model. So if you give SLX file to someone else, it will receive also this script. And this is very nice way, yes, but it's not that obvious. And also, when you design, you should refer to those variables. And on the first time, MATLAB will blame that those variables are unknown because they get initialized when you run the model. And this is kind of inconvenience compared to the separate script. Okay, now what we should do when we have adjust here, because this quiescent frequency must be equal to this FQ variable, and sensitivity must be something, what was here? Let's look, I already forget. It was like K0 divided by 2. I have this K0, no, K0 divided by capital T. Make sure that those variables are defined, because ASTIL has used lowercase letter for this. Initial phase must be, I don't know, ASTIL put P divided by 2, but I don't know if it is really necessary here.
You put that in last class.
Okay, so maybe it's a good idea, but I should mention this in this case also. And the sample time must be this T, yes. This is the most complex blocks, yes, because this is like 3 parameters. Other blocks are just very simple. Okay, save. Theoretically, now we should add this reference source. So we go to the library and find this sine wave source. Just do not use this sine wave because it's bad. Go to down and use this steppy sine wave because it's much more better block. It does the same as first plus many other things. And here you say that amplitude is 1. Frequency must be little bit changed from the FQ, because FQ is frequency what we really need. And this PLL is already generating FQ. That's not interesting. We will disturb it little bit away by 4th part of the bandwidth. So if our bandwidth is B, so we just bandwidth divided by 4 or something like this, we little bit disturb it aside. So if, for example, if we have like quotient frequency 100 Hertz, yes. Now I'm using ASTIL numbers, doesn't matter. And that means that we off tune by 2 Hertz. That means like it works like, no, but even not 2, but half Hertz because we divided by 4. So it is like we use 0.5 or 99.5. So it's it is 100.5. It's like we are detuned by ½ hertz, and the PLL must attach us to the initial frequency. We can try also bigger offsets theoretically, because it must catch even on the like B or something like 2 hertz offset, but it will be much more difficult, because more we go away from this quotient frequency, more difficult for the PLL is acquire this synchronism. Phase offset, okay. Real, trigonometric, sample time must be this capital T, of course. Samples per frame must be 1 sample, because it doesn't work in some frame mode. Theoretically, that's okay. This is already working model, but we will not see any outputs because we do not have any oscilloscopes or something. Yes, but if we now run, it will run. And you see no errors. That means that everything is fine. What we do now, we connect the scope here. We go to the library, select in sync the scope, put it here. We need 2 input ports indeed, yes, because, and we also have to flip it, because our signal goes to from the right to left. And here we will connect this reference signal, because we will compare output from the PLL. But because PLL generates here 90-degree shifted signal compared to the reference, we will need some phase shifter here to shift the phase by 90 degrees. And the simple thing what we could do here is just put derivative, because derivative of sinus is cosinus and derivative of cosinus is sinus, roughly speaking. So we just put derivative, or of course we could put also some phase shifter here, but it's not necessary because it's much more complicated device than just derivative. Derivative is super simple block. Just find discrete derivative. So we go here, but we will put this derivative in the middle. Just. And here we must just enter this gain value. Gain value is already written into our lab work description. This is approximately minus FQ divided by 5, no, minus 1 divided by 5 times FQ. But it could be necessary to adjust this little bit to get the same amplitude, because the drawback with this derivative is that it doesn't only changes the phase, it changes the amplitude, unfortunately, because this amplitude depends from the frequency as in normally, and that's why we have to correct it by the gain value. And as I have seen that I still have something like 643 or something like this. Okay, let's put 6 or something. Will be anyway much closer to what is necessary. And now, if we run, we must see, we also could also configure the scope, because we need at least say that, okay, we could say that it open at simulation start because it's really convenient. and the time must be equal to the, let's say, 20 periods of our oscillator. So that means this is 20 divided by FQ. That means this is like, because FQ, 1 divided by FQ, this is a period of the sinusoid which is generated, and the 20, that means that we will see 20 periods. And also here in the simulation also could be good idea to put this number. Because in this case, there will be not any redundant running, and scope will not rewind, and we will see everything correctly. Because if those times are not synchronized, for example, it could be happen that your simulation goes past visible time in the scope, then it opens new page, and you will not see beginning of your process, and that's not convenient. So that here, for example, that means that this is, we need only 0.2 seconds to see what goes on. Not 10 seconds as it was at the beginning. So I made some mistake. It just started and finished. So what was wrong? Time. Okay. FQ. I think I made mistake here. Okay, just make here stupid mistake. Must be the same thing, 20 divided by FQ. Okay, now it's works. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like 20 periods. Even we could simulate just 10 periods, but we need maybe to have better control. You see, and the amplitude is a little bit different, but it's anyway, it's enough that we could compare that indeed it synchronizes. And also maybe if you put longer simulation time, like 200, yes, then it will redraw the scope 10 times because it's 200. Then you will see that it will not diverge. Yes, because it could happen that it will synchronize and then go away after a while. But see here, we see that it keeps synchronization forever. You will just, it has acquired synchronism and keeps running synchronized all the time. So this PLL is working correctly. And the only problem here is that this generated signal, this blue one, is not really sinusoidal. Yes, and if you go here, let's check. This yellow is sine wave, yes, and the blue one is generated by the PLL. And now the purpose, one of the tasks is also that you have to measure this control signal. We didn't this in the last, during the lecture, so I maybe mentioned this, how to do it. So maybe I will reduce this to 20 back. And for the scope, I will add one more input. Adjust 3 ports. And now all three ports will be drawn in one axis. And this is not convenient, yes, because it will like, okay, we can draw it and I will show that it's not convenient. We need this control signal here because we wish to check how this VCO gets driven. This is very interesting. And if we run now, we will see this driving signal. But this driving signal is extremely small compared to others. That's why we do not see anything. And that's good idea to split. Put layout and say that we have two axes. And now you clearly see that this reference signal is sinusoidal, but this generated, you see something wrong. It's not that nice. It's a little bit skewed. This is a problem of the PLLs, that they do not generate very clear signals. So, how to move this blue to the separate? One of the solutions could be put 3 cells and then use auto scaling here. Then we will see this control signal. You see it, there is a DC component. Yes. And also some high frequency component not suppressed by the filters. This is a bad thing, yes? Because if filter would suppress this small oscillation inside this control signals, this would be perfectly sinusoidal. But because of the small oscillations, it is not sinusoidal, but somewhat sinusoidal-like. But now we will look to the total harmonic distortion, and we will see that it has some noise inside it. So, not noise, but some distortions due to some harmonics, roughly speaking. So what we could do also, we could join those two together. How to do it? Unfortunately, MATLAB doesn't allow to control which signal goes to which axis. And the only way is to say, oh, maybe it's possible. Now I started to think that if I go to style, okay, it's nice. It means that it could be controlled. So just we say layout, we have 2. And now we go to the style and say for this second signal, this. Oh no, we cannot move it to another display, so it doesn't work. So the only way, so it always groups together last 2 signals. The only solution in this case would be just delete this and move it to the last 2 ports. it will become a little bit ugly, but now this control signal will be in separate sub-window. Yeah, and now we can see this is the result we would wish to achieve because we see this control signal. Now let's check finally one thing, and then we will maybe okay, let's check the last thing. VCO input signal we have checked, number 6. This is the number 6 point in the lab work description. This is a waveform. Now the frequency synchronization range. Now we could also check at which range of the frequencies we have this synchronization. For this, we have to play around with this frequency. Let's say we could put B divided by 2 and look if it still synchronizes. It still looks okay. Okay, let's increase. Let's put B here, so it is even bigger frequency offset at the beginning. Okay, you see, if there is no still, we can run for longer time and check if it is successful. No, it's successful, just takes more time. Okay, how about 2B? Or you can put some numbers here as well. Like now we have 4 Hertz offset. Okay, it takes very long time, but it synchronizes. And if, for example, we look, we cannot notice any changes, but they happen. Okay, let's put 4B. Okay, it synchronizes anyway, after very big time. Okay, 8B. It's a surprisingly big synchronization range. Okay, 8B doesn't work. You see, it doesn't catch anymore. So it means that like 4B was working. How about 6B? Okay, 6B also is not good. Okay, like 5B, maybe it's okay. So it is like 5B, this is 10 Hertz offset. So that means we could offset because our central frequency is 100 Hertz. Now we can go from 90 Hertz until 110 Hertz in the reference signal, and our PLL will still catch the signal and will be perfectly synchronized to this band of 20 Hertz offset. This is surprisingly big. Yeah, it takes time, but you see it finally goes. And maybe if you look, if you now adjust this and say that it is 200, maybe we will see some funny pictures here. You see how this PLL jumps before synchronization to the, and here it goes to the some stable state, yes, some So this takes like 0.6 seconds to acquire synchronization to the reference signal. And now we have offset like 10 hertz, yes? Like here we have, this is 100 hertz because it's FQ. And this is 110 because I can put explicitly 110 here, and also it will be working. Like you see, it is the same, like 10 hertz from the top. Let's now check if it is synchronizes from the bottom. Let's put 90 here. That is 10 hertz below this central frequency. Okay, it's also approximately the same process, like a little bit different dynamics, but also like, so that means that this PLL, I did work already for the Astil because he is very good student, no problem, and measured this acquisition bandwidth, this synchronization range. This is point number 8, and for his student ID and parameters, the synchronization range is plus minus 10 hertz. That means that it's able to work from 90 hertz until 110 hertz. At any of frequency in this range, this PLL will catch the signal and follow the frequency and the phase. And this is very good result, by the way. I didn't think, I just before thinking that this capture range is like around the B, but now I see that it is even 5 times B. It's working. Okay. And now also we could say about the time. It's like 0.6 or like, okay, about 1 second to acquire the full synchronization. Like you see here also some small, you see the picture here is a little bit different, then it becomes stable, like maybe it takes maybe 2 seconds or 1.5 seconds to acquire full synchronization. This is like very difficult to say at which moment it becomes completely synchronized, but let's say about 2 seconds, yes, to have full synchronization. Next thing, what we could answer, this is number 10, measure amplitude spectrum of the generated signal. So what we do, we just measure the spectrum of this blue signal. For this, we will need spectrum analyzer. Yes, we go and find the spectrum analyzer. So guys, are you here? Because I didn't hear anything from your side.
Yes.
Yes, Professor.
Oh, good. Okay, because maybe I was afraid that everything has disconnected and I'm talking with myself.
No.
No, we are there, Professor.
Okay, good. So we just find spectrum analyzer, but do not use this audio toolbox because sometimes it provides, and we use DSP system toolbox, and we measure this signal generated by PLL. So it is actually, we can take it from this point or this point. It doesn't make big difference. But let's connect it here. In our lab work is connected also at this point. In this lab work description, I mean. And we also could do the dirty trick and measure spectrum of both signals. Here, if I go file, number of input ports, I could say 2. And then I will also could feed this reference signal to the spectrum analyzer as well. Maybe now I started to think that it could be more consistent to use such a connection, to have this spectrum analyzer and the oscilloscope completely parallel, to not have any, let's say, dirty tricks here. But this derivative, of course, little bit will make high pass filtering, and it will increase amount of the harmonics into the signal. And what is important here is that we measure spectrum not from the beginning, because during the synchronization, it will generate a lot of components now, and we measure, let's say, something like maybe let's use some 10 periods for the spectrum analysis. So for this we will need, okay, let's use power, no problem, spectrum, inherited, Welch, and here full frequency span RBW. Instead of RBW, we should put RBW. This is a resolution bandwidth, and this is opposite to the time of measurements. For example, smaller RBW require longer time span for the analysis. And if you wish to analyze exactly 10 last periods of the generated signal, we could take here just FQ, because quotient frequency, and divided by 10. In this case, it will be like exactly 10 last periods. Okay, let's run. Okay, what we see here is that this blue signal is relatively good. So you do not have any harmonics even inside at this final state, because we have like minus 200 dBs. Maybe if we zoom a little bit this area. Okay, and you will see harmonics here, you see. This is nasty beast, yes? Because original signal, because this is because of the very high sampling rate, we are not interested in such high bandwidth. So let's use not full frequency span, but like maybe again here we need like maybe first 10 harmonics. So it's like quotient frequency times 10. This time it's multiplied. And even we could also say that we do not need double-sided. We could live with one-sided spectrum, yes. Okay, and this is a bug of the Simulink, which always has this center frequency non-zero. But what this center frequency in this mean? because if it is not double-sided, there is no parameter center frequency. In this case, the center frequency must be FQ times 5. And this is really, really strange setup, because on my expectation center frequency is still, but okay, because it's one-sided, maybe it's like acceptable. So now we can easily observe the harmonics. Yes, and you see that this yellow is original signal spectrum, so it's clear sinusoid without any noise inside it. But PLL has generated, okay, visually, yes, visually, if we look, signals look pretty same, yes, but you see, this is kind of dense in this sinusoid here. That means it is not clearly sinusoidal. And this is a big problem, because if you now feed this signal into the receiver, for example, for the down conversion, all these harmonics will create byproducts. And those byproducts will get mixed with this useful signal, and will decrease the sensitivity of the receiver and create some other problems. And that's we are interested in maximally clear signal from the PLL. And of course, we have not, the purpose of our lab work was not to do this, but you see, this is huge harmonics, and this is like very noisy signal. Of course, if maybe we could decrease this offset, like instead of 9 Hertz, we will use 99 here, I believe that signal could be clearer. No, you see, it doesn't, harmonics don't disappear. And if you look here, you still see this blue has some shape problems, little bit, not much. But if you look to the logarithmic scale, because this is a logarithmic scale, if you look to the linear scale, yes, like for example, RMS here, you see those harmonics are tiny. They are like 20 times smaller than the main component. But in the logarithmic scale, they are noticeable. And this is, and you can measure this. How to measure? You go to the measurements here. There is measurements button somewhere. Distortion measurement, it's called. And if you go to the distortion measurements, it will appear at the bottom. And here you will see this THD. This is total harmonic distortion. And if you run, so it's not enough harmonics, like 6 harmonics, we need larger frequency span. Either we decrease number of the harmonics, but we could increase the frequency span, like let's say 12, okay, or even 14, because in this case we are pretty sure that it will be 6 harmonics. And still Okay, but because we are measuring this yellow signal, it says that it's perfect. Yes, THD is 0, that means it's perfect signal. But we have to analyze this blue one, discrete derivatives, the signal coming from the PLL. And here you see the first harmonic is 27 dBs. And second harmonic doesn't exist, but we have third harmonic minus 20 dBs. This is like very strong. Like only you see like less than 1 dB compared to the first one. Okay, but it's wrong. It's really like, okay, this is 50 dB. Yes, not just, this is 27 minus 27. So it's like about 50 dB difference. And then again, like 30 dB is a fifth harmonic. And it leads to total harmonic distortion like 5%, like 448%. This coefficient, this is very important parameter and says about the purity of the generated signal. Less is this number, the more pure sinusoid is generated, yes? And for communications, purity of sinusoidal signal is very important. Also, it's important for the acoustics. Also, yeah, I believe even in this power electronics, if you have this inverter, it's also important that you do not have very big THD for the generated sinusoid, because your inverter in this case will generate a lot of noise for other electronics, and this noise will propagate through the power supply to the, for example, your TV set, and then it will work very bad and even can burn out if you have very bad inverter. Okay, that's approximately it, what we can do in this lab work. Maybe I'm happy that I have shown this, because we will have new video for the coming years. Hopefully it will not be necessary for the lockdown. So, but I don't know if we have some questions, or maybe I can just we can make some pause, or even you can work on your own. But I have nothing to say about this stuff. Okay, I will save all this stuff, but I don't know, this model anyway will be deleted after the reboot. But you can send this over the network to somewhere else, yes, because you have, these machines are, we have web browser, you can go to the web browser on this AnyDesk machine and upload your files. Or even, I think AnyDesk allows to copy and paste files. As much as I remember, someone have said that it's possible. That like, but how you can do this?
It's just we can copy paste.
Yes, if you go to File Manager, like this, and yes. I go to the documents, and I copy the script, yes. Okay, I need this too, for example. Copy. Okay, let's check. Then I go to my Macintosh, go to some desktop, for example. No, it doesn't work for me.
No, but in Windows it will work.
Okay, maybe it's because of, maybe I have disabled something, because there was an option, File Manager or something like this. Because I was doing something. tunnels, control, allow. File transfer. Please copy fields to the clipboard. But this is like in opposite direction. What is this? This is some already, this is a request from other people. Okay, this is like someone is asking to connect. And what will happen if I accept?
Professor, it's already connected. Actually, it was my request there.
Yes, but what will happen if I accept? It means we two will be working on the
So
same.
actually, usually it works like the request will be gone to the remote desk and you'll have to accept it, but I don't know how it already worked. The first, it doesn't ask for any approval. The remote desk was connected automatically.
But strangely, is it okay? Because okay, but if it doesn't see that it's busy, it cannot switch, or it will ask me to log out or something, or will even throw away me. Maybe it's like this. If I accept incoming connection, it will kick me out and connect you. Because we tried two people connection to the same desktop and it didn't work. Okay, but how to transfer files? Still mystery. Okay. Copy to.
Professor, you can paste in your host computer so that we can able to see and we can copy from that.
What you wish to copy?
No, that thing you are saying, this thing.
No copy. You should do it by yourself.
Yeah.
But you can ask till he has file. For some not big amount of money, he can sell you this model.
What? No. I didn't do it this semester, but I did it in last semester. The sending with Romans.
Because you do not need any files. This is easy lab. You can easily, it's much more easier than the next one, for example. So I think I will leave you. Now you can do lab work if you wish on your own. If you have questions, you can ask now. Otherwise, I will disconnect and go to the other things. Because I don't know. And if you have something not working, I can try to help you. Then you have to share, of course, your screen, because I cannot come to your, even I cannot connect to your desktop. But it could be really convenient if few people could remotely connect. But the case, it was the design of this idea of this AnyDesk was that the person is sitting at the computer, yes, and someone else connects remotely and helps him. Okay, yes, but it's a little bit awkward that everyone is connecting remotely and there is no local person.
But we use the same variant, but for me, the total harmonic distortion was different.
Because maybe you have a different simulation time. Or because it depends from the different parameters. First of all, this simulation time, because now we have 200 FQ. If it is shorter, then it
Yes,
could be.
it is same for me.
Okay. what is the frequency offset?
It was 99.
And what is your THD?
Mine was 20, just a sec, 26.84.
Oh, this is too large. Okay. Could you share it?
Yeah.
No, no, no. 5.2. Is this THD is at the bottom?
Oh, this one.
Yes. This is
But
like this is the
different.
level of harmonics. Okay, it could be, I don't know, some specific of the simulation of the version of the MATLAB or something like this. Not big deal, 1%. Because otherwise it looks very similar as mine. The spectrum is approximately the same, and it could be different MATLAB versions, for example.
Yeah, it is
Or Windows
2019.
Linux version, I don't know what could. It of course very strange that it's so big difference, but maybe it's something. But it looks like okay. It's like
No, maybe it's because I think you used 6.6. I used 6.3.
yes. This is a problem in reality because this acting as a filter, and actually the more correct way is connect directly to this VCO output. But you can try this because
Okay.
in this case this harmonic distortion will be a little bit smaller if you connect this spectrum analyzer to this -1 block instead of this filter.
Okay.
But then it will be like little bit strange that
Like here?
scope is yes. And run now. It will be a little bit different, smaller THD, I think. Because this derivative increases level of harmonics. Yeah, it's like 1.7, yes, now.
Yeah.
Okay, you see, this is even, it is much more bigger impact that I ever imagined because this derivative works as a high pass filter, yes, and it increases higher frequencies, and that's why this harmonics gets amplified.
Oh,
And that's why maybe it's not used, because in reality, where is the problem? Because when you are generating your signal, you will need this 90-degree shifted version of your PLL signal. And then there is, if you look, for example, to this book about RTL-SDR, they use 2 PLLs in parallel with different phase offsets, not 2 PLLs, but 2 VCOs. One VCO is connected to the phase detector, and another VCO is running freely and generated this 90-degree shifted signal. They do not put this P divided by 2 into this, and then it generates. And this is also, if you stop sharing, I would show you this solution because it's a little bit interesting for me as well, how we can overcome this problem with these harmonics. This could be a solution like this. We create one more VCO. And instead of this block, we work with this. But in this VCO, we do not P divided by 2, but put 0. That means that it will generate clear cosinus. And this is, of course, more computationally intensive. And it seems like it has exactly. Okay, that means that we will need still this -1 here. Also. Okay, let's check. Now it's, you see, it's perfectly again matching. And the THD is 1.4. So it's much better solution. Turns out that instead of this derivative, 2 VCOs are better solution. Signal is much more clearer. Okay, like we decreased. Okay, harmonics are here, but they are like you see now it's like minus, we just saved approximately 10 dBs. Like this third harmonics now is -36. And the first is +26, it means like 60 dB difference. But this is, okay, it's, you cannot do it this way because it's like, but how it could be -36? Because I clearly see that this is like -10. Like, but this is maybe relative to this. It looks like, yes, it's like relative to this +26, it's -36, like -10. Yes, really. Okay, this is this, that means this third harmonic is -36 dBs compared to the first harmonic. Okay. And yes, maybe in the future we will use this setup. And if you wish, you can use this setup in your lab work. And this is, I think it's better a little bit. But 2 VCOs. And the only thing, what I think is that if we could do some optimization and remove this -1 here and use here minus, but I think it will not work. Oh, it works. But we still need okay, if we put here 90. Is it still? No, it's okay, yes. It's a little bit lagging, but works. It's interesting that if I remove -1 here, it will not work. And there is no way. Okay, but I can do this. I can do dirty trick. I could put here minus pi. Yeah, I have improved the PLL in several aspects. Get rid of one block, but one block comes. Okay, now it's simpler. Okay, this is a ultimate model of the PLL. So what I did, yes, guys, if you wish, I repeat. I replace this -1 by this shifting by -p, all faces. In this, yes, it was previously pi divided by 2, but I put minus pi divided by 2, so I shifted by, because this -1, what it actually does, it shifts the phase by -180 degrees. And this second VCO in this case must be, instead of 0, must be minus pi.
Okay.
Fine. So I'm a little bit happy that I have learned also something from all this stuff. Okay, now a future lab work for the amplitude modulation, we will also use 2 PLLs, maybe because it will generate more pure signal, because this derivative is not that good idea. Yes, but I think this PLR is quite sophisticated. This VCO is quite sophisticated block. If you go here, for example, look under mask, you will see what is inside here. You see, this is, and this is, if you go here, okay, no, this is kind of ready block, but this is by far not that simple as a derivative. Okay. Then I stop sharing, and maybe I will now stop the recording of this lab work if you do not have any questions, because I will not put some space and silence into the recording. And I think now we can stop. It's like 3 o'clock. If you wish, you can do it for 1 hour. And even I think no one needs these computers. Even you can do this at any other time, except I think
Sure, okay.
it is only used on the Tuesday mornings, yes, in the 10 o'clock. But anyway, if it is busy, you will not be able to connect.
But I think my lab is over, right? I have found the harmonic distortion.
Yes, you just have to put everything into the report and upload to the Orthos.
Okay.
I just planning to look to all these labs, but it's too much work. Okay,
And for the lab 2, I didn't use the one mentioned in the music file that is in the lab computers. I just processed the audio and converted to mono, and in that specification. So is it a problem?
No, I think what lab 2 was this QAM, yes?
Yes, but in lab manual it is specified that we should use the one in lab computer, but I can't access to the lab computer on that day. So I just download one music file and convert to mono 128 bits. And I just
No
use
problem.
that one.
No problem. You can use any audio files as you wish. No, if it works, just only if you, because if you use stereo files, it could be problem.
No, but just I converted it to mono before I used it.
Okay, but another solution would be also use this, because if you use stereo, it use two outputs. And one of the outputs, you just leave this not connected, and also it works. But I think it will increase the load for the computer if you use stereo files.
Oh, okay.
And by the way, those computers which we are now connected have software-defined radios also connected to them. So you can also, for example, if you wish to do the FM receiver or something like this, you can actually do this because computers have these software-defined radios already connected to them. Or you can do something else if you wish. But in next lab, actually we will do this on the next week. That means because we do not have any theory, we will do lab on the, we will use our amplitude modulation receiver, which we was using in the lab 3, but we will replace this envelope detector with PLL, yes, and we use PLL tuning to this radio station. And I will run the music again on this, on the one of the computers remotely, and you will try to catch this radio station with the music and check if PLL is auto. You will even see that it automatically tunes to the station if you are close to it. All modern receivers use this technique. That's why you do not have to tune very finely your receiver. Even this amplitude modulation, this shortwave and FM receivers 400% uses PLL. Even PLLs in FM are used for the FM demodulations, and PLLs are used a lot, by the way. This is one of the common building blocks. That's why we are paying attention to it so much. And that's interesting also, I think. Okay, guys, I'm going to have some lunch, but you can continue, okay?
Okay, Professor.
Okay, then I will now disconnect. If you have something, maybe, okay. Okay, if you have some questions, maybe then we will discuss it later and something like this, or you can send emails and I will connect back to Zoom. Okay.
Okay.
Okay, Professor.
Okay, bye-bye.
Thank you.